In this video, we're going to be talking about surface integrals. So we'll be integrating functions over surfaces. Now recall in R2, a parametrically defined curve would be the following, where you have one parameter t and two dependent variables, in this case x and y. Now when we move up a dimension to R3, now instead of it being a parameterized curve, we have a parameterized surface. And we have, if you notice, r of uv, we have two parameters where we used to have one, and we have three dependent variables where we used to have two. Okay, so we assume that this these parameters u and v are going to vary over some region r, so we'll say that u varies from a to b, and v varies from c to d, and this is over r, d. So this is, we'll define this as this rectangle R. Okay, so R, just quick definition here, is u comma v, such that u goes from a to b and v goes from c to d. Okay, now when we take the parameterized surface here that uses these parameters u and v, what we end up getting is this smooth surface in R3. So as u and v vary, now we're in R3, we have this smooth parameterized surface. Okay, and we'll call this surface S. Right? So this is R of u, v. So as u and v vary, we get this surface. Alright, now the surface integral is what we're going to define now that we have the idea of the smooth parameterized surface. And so the surface integral is going to be the double integral over S. So we have surface integral, and this is going to be of our scalar valued function f over S, which is our smooth parameterized surface. So we have the double integral over S of f of xyz ds, and this is going to be equal to the double integral over R of f, where the f is comprised of x of uv, y of uv, and z of uv. And then we're going to take this and function and multiply it by the magnitude here, and the magnitude of the cross product of t sub u cross t sub v. So what this is over here with this magnitude is this is the cross product of these tangent vectors, where t sub u is, well, let's define it here, where t sub u is the partial derivative of r, our parametrically defined surface S was defined, if you recall from before, S was r of u, v. So the partial derivative of r with respect to u, and then t sub v is going to be the partial derivative of r with respect to v. Okay. Now just a quick note here. If the function f of xy, so if f of xyz equals 1, then all you're doing when you evaluate this surface integral is you're finding the surface area of your surface S. So if f is equal to 1, this is just going to give you surface area. Okay. Now before we get into an example, let's go ahead and just define some parameterizations for specific surfaces that you might come across. So first one would be a cylinder. And so for a cylinder, a parameterized or parametric description would be r is equal to a cosine u, a sine u, comma v. Okay, and this is going to be where u varies from 0 to 2 pi, and v varies from 0 to h. And you can think of h as the height. And a is just like going to be equal to the radius. So that's a cylinder, parametric description of a cylinder. Now for a cone would be described as r is equal to v cosine u, v sine u, v, with the same limits for u and v. So this is also part of the cone. Then we might come across a sphere. So for a sphere, we have r is equal to a sine u cosine v, comma a sine u sine v, comma, and let me just write it down here, a cosine u. Okay, so this would be a parametric description for a sphere, and this time we have u going from 0 to pi, and then v is going to range from 0 to 2 pi. Okay, and then the last one we'll look at is a paraboloid. So for the paraboloid, we could describe this as r equaling v cosine u, comma v sine u, comma v squared. Okay, and u is going to vary from 0 to 2 pi, and v from 0 to the square root of h. Okay, so we'll use these, and actually one of these in the next example. We're going to look at a cylinder. So we want to find the area of the surface. So for this example, we have a half cylinder, and it's going to be described by r theta z, such that r is constant and it's 5. Theta is going to range from 0 to pi, and z is going to range from 0 to 8. Okay, so what we want is we want the area of this surface. Okay, so this is the question. This is what we're trying to figure out. Now, we're going to go ahead and let u be equal to our parameter theta, and v, will set that equal to z. Okay, so our surface can be defined as r of uv, and just a moment ago we described had a parametric description for a cylinder. So it was a cosine u, so that's going to be, a is our radius, so 5 cosine u. Then we have a sine u, so 5 sine u, and z, which is v. Okay, so now we need to evaluate the double integral over s, and because we want the area of the surface, we're going to just evaluate this integral where our function is equal to 1. Okay, so we have, by the definition of surface integral, this is equal to the double integral over r of 1 times the magnitude of the cross product of the two tangent vectors, one with respect to u and one with respect to v. So this is going to be times that magnitude of the cross product of the tangent vector. So let's work that out real quick. So right here we're going to look at the partial derivative of r with respect to u. So that this first component is going to be negative 5 sine u. Okay, and then right here we're going to get 5 cosine u, and then this is going to be 0. And we're going to cross that with the partial derivative of r with respect to v. So let me just write it down here. So now this is 0, 0, 1. Okay, we're going to find the magnitude of this. Alright, so first let's focus just right here on this cross product. So this just right in here, let me highlight it. I know it's kind of hard to see because it's on 2 lines, but we're just focusing right here on this cross product. Okay, so we have I, J, K. We're going to just evaluate this cross product of -5. Let's space this out a little bit. -5 sine U, J, 5 cosine U, K, 0. And then we have 0, 0, 1. Okay, so basically we're just going to find the determinant here. So for the I component, we have 5 cosine U times 1, which is just going to give us our 5 cosine U, minus 0 times 0, so we don't need that term. That's our I component, minus our J component, so that would be -5 sine U times 1, so -5 sine U, minus 0 times 0, that's our J component, plus our K component, which is going to be -5 sine U times 0, minus 5 cosine U times 0, which is just 0. Okay, so this whole thing ends up being 5 cosine U I in the I direction, plus 5 sine U in the J direction. Okay. Now, we still need to find the magnitude of this. You might be able to just look at it and tell what it's going to be. So the magnitude of the cross product that we just evaluated is going to be 5 cosine U squared plus 5 sine U squared, which is just going to be 5, if you can see it. So 5 squared, cosine squared plus sine squared is 1 by Pythagorean identity. This is just going to be 5. Okay, so back to our double integral. It was over our region R at this point, and it was 1 times this magnitude, so 1 times 5 dA. Okay, now let's go ahead and put the limits of integration on this double integral. So we have our integrand of 5. Now we had that U was our theta, and theta was ranging from 0 to pi, which we wrote down before, so U goes from 0 to pi, so to U's first, and then outside V was ranging from, well, V was equal to Z, and that was ranging from 0 to 8, so dV. Okay, so let's go first with the integral of the inside here. So we have integral of 5 with respect to U. This is going to be 5U, evaluated from U is 0 to pi. So we end up getting our integral 0 to 8 is just going to be 5 pi, because this second term turns into 0. This is dV. So now we integrate with respect to V. So this is going to be 5 pi V evaluated from 0 to 8, and plug in 8 and we get 40 pi. Okay, so this is the value of our surface integral, which represented the area of the surface. So this is the area of that half cylinder that we defined at the beginning. Okay, so this example, and what we talked about for this first definition for surface integral, was when we had to parametrically define our surface. So now we want to do the same thing, but we have our surface integral, and we're going to explicitly define the surface. So the surface integral of our scalar valued function f, again, over our smooth curve S, but this time we're S, so we'll say over S, where S is explicitly defined. So we no longer have to find the parameterization. Explicitly defined. So the surface integral is going to be, oh, let's make a note about s real quick. So s is going to be z equaling g of xy, and this is for x comma y in our region R. Okay, so our surface integral is going to be the double integral over s of f of xyz ds. So that hasn't changed. And this is equal to the double integral over r of f of x, y, and now z is equal to a function of x and y. And then we're still going to multiply by the magnitude of the cross product like we did previously, but when you evaluate that with this explicitly defined surface, you end up getting the square root of z sub x, so this is the partial derivative of z with respect to x squared, plus the partial derivative of z with respect to y squared plus 1. Okay, so this is the form of our surface integral when our surface S is explicitly defined. So we want to look at the explicit definition or equation for the surfaces that you might come across most frequently. So again, like before, we considered the cylinder. So now the explicit description would be x squared plus y squared equals a squared, and we have that z goes from 0 to h. For our cone, we have x squared plus y squared equals z squared, where z again goes from 0 to h. And the next thing we had looked at before was a sphere, and this is defined as x squared plus y squared plus z squared equals a squared. And then lastly, the paraboloid is going to be defined as x squared plus y squared equals z. And this is for z from 0 to h. Okay. So now let's go ahead and look at an example using an explicitly defined surface. So our scalar valued function f of xyz is this time is going to be equal to 6xy, and our surface S is going to be the plane, which is defined as z equal to 6 minus x minus y in the first octant. So the first octant is basically where x, y, and z are not negative. So if you wanted to just get a picture of what was happening here real quick, we have our three dimensions, and we have this plane describing our surface. And so what we end up getting, if x and y are 0, we go to 6 on the z-axis. If y and z are 0, we go to 6 on the x. Same thing for x and z being 0, we go to 6 for y. And you end up getting this surface here. Okay, so just imagine it like this triangular wall, and it's popped out from this region in the back is open. Okay, so we want to evaluate the surface integral here. So let's go ahead and write that. So we want the double integral over s of f of x, y, z ds. This is going to be equal to the double integral over r of f of x, y, and then z. Remember, it was defined as 6 minus x minus y. And that's going to be multiplied by the magnitude of, just to remind you what we had just looked at, it was the first component here was the partial derivative of z with respect to x. So let me just remind you, z was 6 minus x minus y. So the partial derivative of this with respect to x is negative 1. So negative 1 squared plus the partial derivative of z with respect to y, that's also negative 1. and it was plus 1. Alright, so if we simplify what we have going on here, well, our function was given. F was, let's leave the space here because we're going to fill in our limits. F was 6xy, and if we simplify this square root here, we end up with square root 3. Okay, now going back to the surface that we drew a moment ago, if we evaluate this integral, the inside, with respect to x, then x, let's just redraw it really quickly. So for x was going from 0, it goes to 6, but if we write this in terms of y, so for this region, this surface that we just drew a moment ago, rough sketch of the surface, so x, this is the x-axis, went from 0 to 6, but if we write this in terms of y, x goes from 0 to 6 minus y. Okay, you can go back and you can just solve this, set z equal to 0 and solve for x. So if z equals 0 and we solve this for x, this is a minus, solve for x, we end up getting that x equals 6 minus y. Okay, so x ranges from 0 to 6 minus y, and then y ranges from 0, and we'll just use the constants here, to 6. Okay, so we'll evaluate with respect to y second. Okay, so the inner integral is going to be, when we evaluate with respect to x, this is going to become x squared over 2. So the 2 divides with the 6, and you end up getting 3x squared y square root 3. And this is from x equals 0 to 6 minus y. Okay, so let's go ahead and plug in 6 minus y. When we plug in 0, it's just going to make this whole thing 0. So we end up having the integrand as 3 times the quantity 6 minus y squared times y square root 3. Now if you FOIL this out and simplify, what you end up with in here, and let's go ahead and factor out these constant term. So, or constant factor, 3 and the square root of 3. So we have 3 square root 3 of our integral from 0 to 6. FOIL this out and distribute the y. So you're going to get 36 when you FOIL times y. So 36y. You're going to get negative 12y times y. So negative 12y squared. And you're going to get y squared times y. So plus y cubed dy. Okay. So we're going to evaluate this integral with respect to y. So let me just leave it down there so we can see what we're working on. So we end up with this 3 square root 3 outside. This is going to become y squared over 2, so that gives us 18y squared. This is going to become y cubed over 3, so 12 divided by 3, that's going to give us a negative 4y cubed. And the last term becomes y to the 4th over 4. And this is from y equals 0 to 6. Okay, so when we plug in 0, everything's going to go away to 0, so we only really need to focus on the 6. So we end up with 18 times 6 squared minus 4 times 6 cubed plus 6 to the 4th power over 4. All of this times 3 square root 3. Now you can do this with the calculator pretty quickly, or you can just factor out the fact that they all have a 6 squared. So however you want to evaluate this, I ended up just doing it where I said, okay, if I take out a 6 squared, that gives me 3 square root 3 times 36, and then what's left inside was 18 minus 4 times 6 plus, notice if I take out a 6 squared here, I'm left with another 6 squared. So 36 over 4, which is 9. And then we keep going, then we get a 24. This is 9. And what you end up getting when you simplify, 324 square root 3. Okay? So this is our surface integral evaluated over this plane, this surface defined as the plane that was z equal to 6 minus x minus y. Okay, so the last thing that I'm going to mention is just the form of a surface integral over a vector field. Okay, So surface integral once again, but this time it's going to be of a vector field. Okay, so we have, in this case, the double integral over S. So S is a smooth oriented surface. So the difference now is that S has to be oriented. And we have F, where F is our vector field. So it's a continuous vector field on some region in R3. So F, and this is going to be dotted with N ds. Okay, so S is a smooth oriented surface once again, and F is our vector field. Okay, so this is going to be equal to, let's go ahead and write it down here, the double integral over R of F dotted with the cross product of our tangent vector. So t with respect to u, partial derivative of R, remember that, with respect to u, cross with t sub v. Okay, and n here is just the normal vector consistent with the orientation of S. So whatever the orientation of S is, n is consistent with that. All right, so this would be when your surface S is defined parametrically. So again, where S is defined in terms of, let's say our parameters again are just like we've had before, u and v. Now, if your surface is defined explicitly, this changes a little bit, or ends up simplifying, if you want to think of it like that. Our double integral, once again, is going to, so this doesn't change. This is equal to the first form if S is defined parametrically. Now, if S is defined explicitly as z equals g of xy, then this becomes a double integral over R of negative little f times z sub x, so this is the partial derivative of z with respect to x, minus g times the partial derivative of z with respect to y, plus h. Okay, so these would be the forms of your surface integral of a vector field.